I hope I'm audible. Just interrupt me if you're not able to hear me.
You're completely
I
audible.
might have some bandwidth issues here, but yeah, let's get started, I guess. Let me just change the screen a little bit. Yeah. So, good evening, ladies and gents. So, this is a lecture where I'm trying to bring the aspects of astrodynamics that are used within space traffic management. And as some of you may know, that the future of space is kind of governed by the issue of sustainability. And as we have on the roads, as we have on planet Earth, we need to manage traffics in space as well. As you can see in the cover page here, that all the yellow dots, red dots, and the green ellipsoids that you see here are pretty much a danger region. You don't want to interact with them, mainly because these are assets of some other people on the space highway. Having said that, I think it's a good idea to introduce what STM means. And since it's an umbrella term, it's a blanket term, and it's a relevant concept definitely. Since most of the services that we use are satellite based and will soon be satellite based, some of them definitely, be it defense, medical, emergency, connectivity, or even entertainment for that matter. So I guess it's high time to look at what we're going to learn from this particular presentation. Here we go. So in this outline, we are looking at first the idea of certain topics within STM, space traffic management. As I mentioned, it's an umbrella term. And going forward, we would look at data standards that are applied in the industry. The reason why I wanted to do this lecture, which brings in the perspective of industry, is because we might have a theoretical aspect of how we can handle certain mission parameters in space. Since we are all passionate and we are here today, so that means we are more passionate about what we can do in space, right? But there is a standard that is applied in the industry, and it is imperative that we have an idea of what these standards actually stand for and how these are used intrusively or intricately, however you want to see it. Um, then we will look at threat screening. What is threat screening? It's we're looking at potential moments in the space highway that could lead to a collision, that could lead to the Kessler syndrome being realistic, or maybe realization of a gravity movie. It could happen very fast. So a threat screening is kind of the preemptive measure we take normally to check if there is any potential risks in the orbit. Now, then we go into orbital dynamics that are, and this is where the amalgamation of astrodynamics and space traffic management happens from here on. And the orbital dynamics concept that are applied within the view of space traffic management is looked into in this case. Space situational awareness is a fancy term. I'm not going to deny that, but it also means that we are aware of the immediate vicinity, immediate surroundings, and the environment. And that is important if you are not riding a satellite in space. If you're riding, then you are the eyes and ears, and you need to be aware of it. But that's not going to happen soon unless we are able to clear out the junk. And then the future approach. Now, this is a relatively niche field at the moment. Space traffic management has just started in the last 10 years. And as you know, it's relatively a baby moment for space race, the new age space race. So there are some future interesting avenues that can be explored in the future. Having said that, let's delve into what STM stands for. STM stands for Space Traffic Management. And as I mentioned, it's an umbrella term. Um, as you see here, there are boxes which are outlined red in color. There is a reason why. These red boxes are the concepts or regulations where astrodynamics is used extensively from the get-go. The rest of it has a lot more combination of mission engineering, data science, policy, and so on and so forth. Material science also. So if we look at international cooperation, why do we need international cooperation? We can all go our merry way, and because there is more space in space, we don't need to worry about potential collision. That's the common idea. But international cooperation is needed when you're considering space activities are are multi-billion-dollar industry, right? So one nation alone cannot pay for one asset in space. So normally what they do is a collaboration between several agencies, several entities, commercial, defense, governmental, non-governmental, name what you want. So there should be an international playground where they can come together and work on this issue. And as the number of satellites are increasing, there is an increasing need for collaboration between several entities. And one of them, as I mentioned, is CCSDS here. Underneath there is ITU. I don't know if anyone of you here have some experience with mission planning or even with an idea of um, frequency spectrum or something like that, then you would remember that ITU is the International Telecommunication Union, and these are the ones that specify the frequencies at which your mission or your satellite will be operating. And these are important ones because you don't want to cross communicate between different ones and transmit wrong messages, which might lead to potential harm in space. Space surveillance network, as the word suggests, it's basically bunch of radars, optical telescopes, passive radios, who are constantly surveilling the space above us and constantly making note of all the things that are passing up above us, including the meteorites, including the debris, active satellites, God knows what. Then you have regulations. As I mentioned, this is not a single technical field. It is an amalgamation of several policymakers, artists, designers, engineers, and also definitely astrodynamicists. Regulations are, as you can see, there is IADC. IADC stands for Interagency Debris Committee. So India is also a part of it, a major part of it, but it is not an actively ruling member of IADC as US or Europe is, unfortunately. But what they do is that they get together, set up norms and regulations, which helps in modeling the debris environment in near Earth space. And that is needed. As you will see later on in the upcoming slides, and there are a bunch of them, and then you would see that why this debris modeling is important. And IADC actively engages between different agencies, commercial entities, and also the non-governmental entities to collect data from several telescopes, even astronomical. Most people don't have this idea that astronomical telescopes are also useful in collecting the debris data. But the ones that are discarded by the astronomical telescopes that are not useful for capturing the beautiful images that are basically spoiled are the ones that are collected by IADC as well. So they use this data to plot all the potential debris particles that are available in space. Some of you might know what UNUSA is. It's the United Nations Office for Outer Space Affairs. These are the king of policymakers because United Nations often is. And this UNUSA body or this committee actually sets up the standards on which or guidelines on which the mission operations normally take place. Also, guys, if I'm speaking too fast or if I'm not audible enough, please let me know because I can't see any of you at the moment. Okay, Satellite Industry Association, it's basically a commercial entity and it's a commercial conglomerate of several industry partners and agencies that can get together and actually get the mission operations side of thing quite robust. Yeah, but they all function in the same realm of policymaking. Then comes mitigation and remediation. The word mitigation means you are stopping yourself or your assets to have any sort of harm in space, right? Remediation is the harm has already happened. Now, how do you prevent it? So one of the method of remediation, potential remediation, is on-orbit servicing. On-orbit servicing could involve something like refueling the spacecraft, rebooting the spacecraft through some remote methods, or you basically use a tug to push it to some other relevant orbit where it can go because its fuel is gone and it cannot maneuver itself to a newer orbit to perform the mission. So it's pumping new life into the satellites. Deorbiting. When no orbit servicing can be done or rebooting can be done. We push it down either into the atmosphere or push it further into graveyard orbit. What is designed for demise? That's a new term, but that's a term that is intrinsically anchored within the new space industry now, and that's there is a reason for that. The design for demise concept basically comes from the idea that we don't need any satellites that remain in the orbit after their life is done. So it can either perish on its way back into the atmosphere, completely burn up that nothing is left, or it is able to just completely fade away. They just, due to passivation and gas outlets, they just fade off. Certain experiments are being done. It's not completely involved into the new technology, into the new space industry completely. It's being experimented upon, and there are ISO standards that are being built around this design for demise concept. I think it's ISO 24000, and there's a new version that has come out now. Now let's go into the astrodynamical components within these. Astrodynamics influenced components like the space situational awareness. You might be a bit confused on what multimodal trackers are. Multimodal trackers is just a fancy way of saying that you have a radar, you have a passive radio, and you have optical telescopes, and these are all providing you data. That's it. And these are multiple modes of data. One is radiometric, one is optical, and one is active radar system. So you have multiple sources of data, and that's why it's multimodal. Screening, as I mentioned previously, there is threat screening, and we'll look into that a bit later. Catalogs. Catalogs are basically it's a database, to put it simply. Catalogs are basically generated by all the agencies who are observing the space. They have a list of objects that they have observed, and they know where it is, along with its position, velocity, acceleration, its attitude, its current activity, including. So they maintain an active catalog, and these are important for screening, for collision avoidance, for pretty much anything that has to do with space traffic management. Now, COLA is a fancy term again for collision avoidance, but that is mostly used in the industry. Everywhere, if you see any reports, they would mention COLA as the maneuver that was performed. And COLA is a collision avoidance, and one of the primary aspect of it is conjunction assessment. Then you have the maneuver suggestions, maneuver implementation, and restitution maneuvers, which means you come back to the original point where you continue with your mission. Now, why did I mention partly right next to mission operations? There is a reason for that. Every time you perform a collision avoidance maneuver, your mission operations is put on hold. Your mission is put on hold, not operations. Your mission is put on hold. And to get back to its original position, then your mission starts to go again. And that basically gets affected by collision avoidance. And therefore, it is an intrinsic component of STM going forward. Having said that, let's look at why do we need the STM in the first place. This is a fancy graph that was provided by ESA. And you can see that each of the bar is representing 1 year. So after 2000, you would see that there was a bump at the later the later 2000s, and that was primarily because of the Iridium and the Cosmos debris, the Russian satellite debris, and the spike of it introduced new particles into the space environment. Roughly, I think 25 to 3,000, 2,500 to 3,000 particles. And after that, there was few anti-satellite tests that was done by China, and that introduced even more. So given our affinity to perform more anti-satellite tests, we would see that this graph is not going to stop at 20,000 particles. It's going to increase further, and this existing 20,000 particle itself is causing more trouble than it was originally thought of. And there is a reason at the moment why STM is taking its pace, is mainly because most of these particles that you see here are the only one that can be tracked. There are untracked particles in space which are more than 1 million in number, and those fall under less than a centimeter in size, and less than a centimeter cannot be tracked by radar also. because of the virtue of signal principles and basic physics. You can't track them from Earth. So this graph is a bit incomplete, but I think a million number will not fit in this graph at the moment. Okay. Having said that, let's look at the LEO environment specifically. Yes, there is a geo problem as well, but there is a LEO environment which is significantly populated, and these are the three mega constellations that existed, and now there are more cropping up. But this is until 2022. So Starlink had just started from 2019 to be really operational, and you could see that at its initial phase, I think latter part of 2020, it reached almost 100% in risk, and that was just in a week. OneWeb has 300 satellites, and it has already reached 75% risk in later part of 2021, and it is going to increase even further because the race for internet connectivity is significant. And this pushes us to the number of maneuvers that was performed by Starlink. This is again part of the latter part of 2021, and you can see that more than 3,300 maneuvers were performed within 6 months. And this involves maneuver against a debris, maneuver against any other satellite, maneuver against Starlink, maneuver against any God knows what. Next is the Starlink versus Starlink maneuvers. That was more than 85 maneuvers in 6 months, and that's too much. That's really too much. Any maneuver is too much, but 85 maneuvers is still too much. You would see there is an unfamiliar term here called acceptable collision probability risk, or ACPL level, and these are the I would say quantitative values used within space traffic management. Terminology is used within space traffic management that assigns the risk to, or a threat level to, a particular conjunction. I should say that conjunction is an astronomical term, and it's used when two objects are in close vicinity to each other, then in a particular arrangement. And in this case, Starlink had a critical amount of conjunction, which was more than 43,000 within 6 months, 43,042 to be exact. And out of which 35,000 conjunctions were just between Starlinks themselves, not even with any other satellites. It's just within Starlink. So that's how bad the environment is at the moment. Now, mitigation versus remediation. I should inform why this is an important one, because going forward, you would see a lot more concepts of risk mitigation being spoken in this lecture. A little less about remediation, because that's more dealing with orbital rendezvous and deorbiting. So that's a different part of astrodynamics that is used. Within mitigation, there is collision avoidance, design for demise, and international collaboration. Within remediation, there is atmospheric re-entry, on-orbit servicing, and safe end-of-life disposal. I should specify here what design for demise again means. It's material selection, component design, demisable structures like weak joints or specific cut patterns that just break open upon re-entry. Then you have the end-of-life deorbit plan. This is important from two perspectives. One is to prevent any sort of fragmentation events happening in space. The other is to prevent any object from going defunct and being a threat, or maybe just be a very costly trash can flying in space. We don't want that. So that's where the remediation comes into picture. Stop me or ask me any questions if you have at the moment, or I can just continue ahead.
There is one question in the chat about what is maneuvers. That's the current thing that's going on.
Sorry, could you repeat again?
Yeah, what are maneuvers? Or
Maneuvers.
maneuvers? Yes.
So yeah, so imagine you are driving on the road, yeah, and you want to go to some other place within the same road. You have a curved road and you just want to go to the other side of the road. What you do? you just can't leave the steering wheel straight, right? You might as well collide with something at that point. What you do is you apply an effort with into the said car, and that car turns to a particular direction such that your end goal is reached. Now that process that you're doing, that's a maneuvering. Same way in space, if you want to go from say point A to point B, you have to use certain methods to get to that point. And you could use fuel, you could burn engines on board your spacecraft to get to that point, or you could just use some environmental factors, as I'll show you later on how you can do that. So maneuver basically is that effort that you're doing, if I answer that question correctly. Any other questions?
There are no other questions as of now.
Okay. All right, I can continue. All right, let's come to the data standards. This, okay, let me give you the rationale why I wanted to bring this to your attention, because I mean, going forward, I think people who are interested into mission design, mission operations, or even just in astrodynamics, continuing within astrodynamics, you would come across these standards mainly because these are designed with interoperability in mind. So if you're developing a tool that say you want to take in position vectors or state vectors from some particular epoch, you want to propagate it to some other epoch and use it to show a maneuver in space. Sorry for using the word again if it's not clear, but if you want to do something similar to that, then you would need a particular standard in which you can automate it. And that's where the development component comes into picture. Operations. If you are already a satellite owner, or if you are a monitoring entity for these satellites, you would want to have an automated system that can get the data, parse the data, take specific aspects of these data, and get you the output that you want. This is important mainly because you as an operator or you as an entity who is monitoring those assets in space, those satellites or spacecrafts in space, you need to have a common playground. The the operator, you cannot expect the operator to function according to your interests, and vice versa. So CCSDS is a committee, the Consultative Committee for Space Data Systems. They came together. It's an interagency. It's a global organization that alleviates this sort of confusions. So if you have a project that you want, if you have a satellite that you want to launch within say 6 months, and you want to set up a ground station ground tracking system within next 6 months, or whatever, however you want to play around with that, then these are the standards that are already in place, and you just need to plug and play, and you get the operations going on for you. As you can see on the right, there are some colorful scrolls. The one that needs to be of interest to anyone would be the one on the bottom, the pink one or the magenta one, the blue and the green one. So the recommended practice, the recommended standards, and the recommended report, I mean the informational report. So the recommended standards basically say that if you want to get the ephemeris of a satellite, the position vector, epoch, reference frame, and all those things information, you follow the standard. But there is a way to implement that standard, and that's within the recommended practice. The overview of all these processes are given within the informational report. You can go into much detail at your leisure when you have time. You can check out CCSDS publications. There's a whole website dedicated to that, and you can access these documents and read it for yourself when you have time. It's pretty interesting if you want to get into the field of astrodynamics effectively. Now comes the mission operations side of CCSDS. This is, like I mentioned many times before, that it's very important that we have a common playground. Now, the green part that you saw in the previous slide, the informational report one, that's the navigation data message in terms of mission operations. There are several others. I'm not going into those things because they don't use astrodynamical principles within them. Mission operations do. So navigation data messages is basically a compilation of different blue books within them, and they form a particular data set that helps in tracking, helps in orbit determination, helps in orbit propagation, helps in attitude propagation, in collision avoidance, and maneuver planning. So as you can see, the leftmost blue box is called conjunction data messages. Now, that's the CDM when I mentioned previously with regards to Starlink versus Starlink situation that there were 35,000 CDMs. I mentioned this, that there were 35,000 conjunction data messages that were generated. And each of the conjunction data messages consists of TCA. TCA stands for time of closest approach. And this is important because this is the point where there is a potential collision or not. Then you have PV. PV stands for position velocity, or the state vectors that you're getting here. Reference frame. You definitely need to know what reference frame you're working on. And that's kind of the basis for astrodynamics itself. If you don't know the reference frame, you can't do any sort of computation within astrodynamics. So that's important, and that's part of the CDM. You have target and chaser. Okay, this is a new term. Target is your asset. Chaser is the one that is about to collide with you. And this goes in the other direction as well. If the chaser is being monitored by someone, for them, that's the target. And there will be a CDM issued for that particularly. Then there is dynamical models. What do I mean by dynamical models? The gravity, the air drag, the solar radiation pressure, the solid tides, earth tides, and ocean tides. Then you have third body perturbation, anything that influenced the CDM to be generated. So the orbit propagation that led to generation of a CDM, that parameters for orbit propagation is also mentioned. You have relative elements. What do I mean by relative elements? Your missed distance. So imagine you and your friend is walking in the same corridor. You might be walking in x-axis, you might be walking in y-axis, doesn't matter. The closest scalar distance that you encounter, that is also mentioned. That's called a missed distance. Then you have relative velocity, how fast you and your friend were moving across in the same corridor. That's also mentioned here. I'm simplifying it here because it's easier to understand it. But if you read the CDM documents, you will understand it easier because they have explained it. So anyone with non-technical background can also understand it. What do I mean by ancillary information? Any other information like the NORAD ID, the ID of the spacecraft, the COSPAR ID, the launch ID, as well as the launch date ID also present. You have the operator name. You also have the any information regarding if the thrusters were fired or if any maneuver was performed. All those information are provided for CDM. If they were tracked, if not, it's all empty. You have something called orbit data messages. And this is where the interesting part of astrodynamics starts technically, because this is where you could start playing with the state vectors and perform orbit propagation and stuff. Within ODM, you have 4 messages type. Orbit parameter message. This is where they explicitly mention if the satellite has performed any maneuvers. Orbit ephemeris message. This is where they tell you from the date of orbit determination until the time of closest approach. They give you a list of position vectors, position, velocity, and acceleration vectors. So you can actually track it for yourself. Then mean elements message is basically to generate two-line elements. I don't know how many people are familiar with two-line elements here, but it's a method created by Celestrak that can be helpful in helpful for anyone who does not want to create a complex dynamical model and just use a simplified general perturbation model for orbit propagation. So that two-line elements is basically your Keplerian elements, oscillating Keplerian elements, and you can use them for simplified analysis. Orbit comprehensive message is relatively new. They just came up with this in the new version of it, and this one kind of adds all the previous three together. So you don't have to look at individual ones. They just give you one file. Be happy with that. That's how it goes. Then you have attitude data messages. These are your orientation in space, basically where you are looking, where you are pointing to, where your satellite is, how your satellite is evolving in the orbit in terms of its orientation. So those information are provided within ADMs. Tracking data messages is basically useful for people who want to invest their time in orbit determination, because this is the one where your ground systems or your in-orbit systems, which track other satellites, provide information based on the signals, based on the optical information, and you can convert those angular information that you received into visible position and velocity vectors. So tracking data messages helps you in that. Sorry, I heard some noise. Is anyone having any questions?
No, I don't think there are any kind of questions. Even the chat is not having any kind of question.
Okay, feel free to ask, because I think this might be a little bit overwhelming. Hopefully not, but this is just to give you an overview of how industry works. Then, yeah, within ODM, ADM, and TDM, you have similar ones, like I mentioned, and I think you can have a look at it later on in the PDF that was provided. Now let's look at what threat screening is all about. So there is a specified NASA process that they have mentioned in their handbook for space sustainability and collision avoidance. In that, they mention what they mean by catalog maintenance. That's maintaining a comprehensive list of objects, space objects, of all known space objects, including data of each object's current position, velocity vectors, and characteristics. Yeah, basically size and shape and everything. Then you have orbit prediction. Now imagine, guys, your catalog is about 1 million objects, right? You cannot be performing orbit propagation for all 1 million objects at the same time, because you would need a couple of supercomputers to do that. So what they have is a simplified orbit prediction system, and in that they have simplified computer simulation models, and they do definitely use a supercomputer, but it's much more simplified compared to what is needed, what is considered as high fidelity. So in this case, they consider the gravitational influence, among other perturbations. They consider atmospheric drag, solar radiation pressures, and etc. etc. Now there is the third one. There is pairwise and volumetric comparison. What do I mean by pairwise? Let's take the previous example of you and your friend. Now imagine, instead of your friend in the corridor, there's a bunch of guys or girls or whoever it is in the corridor. You are going to collide with them. You're going to move amongst them. Now the system is designed in such a way that your position versus the other person in the corridor is being compared at one at a time. So as a pair, you versus entity 1, entity 2, entity 3, like that. And that will take years to compute. NASA came across a better idea of this. And what they said is that, look, let's create a volume of my object and let me pass that volume through the crowd. Whatever intersects with my crowd, with my volume, is a threat for me. I'll issue a conjunction for that. That simplified the whole approach in the way the industry is working at the moment. That actually leads to the fourth point, which is conjunction identification. So a potential conjunction is identified if the minimum distance is less than a predefined threshold. So if NASA says that, hey, so this satellite has a threshold of less than 100 meters. If I consider anything that comes within less than 100 meters, I'm going to consider it as a collision, potential collision. So I will just look at those objects which are less than 100 meters with me, and then I'll issue a conjunction on that. Then comes collision probability calculation. I'll go into this a bit later. That's I think much better. Then you have the warning issuance. So they develop a CDM the conjunction data message, and then they disperse it out. So anyone who is the asset of that spacecraft can actually have a look at it, because everyone is registered in this portal. Then you have collision avoidance planning. Now this is done either by the chaser, the active satellite, if it is an active satellite, or the target. Either one of them has to maneuver, or some of them just leave it out because they think that it is futile to maneuver at the moment. Let it just leave it. Let us just leave it at that. So there are some potential miss cases here, like the one that happened last week, that there was a Starlink satellite, I think. It was about to collide with a Russian. Oh no, it was a Chinese satellite that was about to collide with a Russian debris, and the miss distance was 30 meters. That's too much, too close for comfort. 30 meters is 3 times the Bluetooth range that you have, and that's how much you were about to. I mean, that's how close you were going to get. None of them maneuvered because China did not maneuver, and of course the debris cannot maneuver. So you have the now let's go a bit deeper into the orbital dynamics. So the overview of the astrodynamical concepts that are used within space traffic management are rigid two-body dynamics, as some of you might have seen in this workshop already. You have the state vectors and the reference frame. It is important that the reference frame is always associated with the state vectors, and that's the data that you work with, because without the reference frame, you will not be able to perform any computation within the astrodynamical sphere. Pardon the pun. You have the dynamical models, like the gravity, like the third body perturbation, solar radiation pressure, air drag, space weather models, and etc. etc. Then you have orbit and attitude propagators. On the right, you could see how the attitude of a satellite is typically created. So you have the translational component, the red arrow, yellow arrow, and the blue arrow, which means you can move in those axes as a rigid body. And then you have the green curved arrow, then orange curved arrow, and light blue curved arrow or cyan curved arrow. These things represent the rotation of your body in those axes. So this is a 6 degrees of freedom entity that you're looking at. And you would need an orbit propagator to work within the 3 translational system. And then you have attitude propagators as well, which tells you based on the rotation rate of the object, how your object is going to evolve, say 10 seconds down the time. Then there's something called uncertainty propagation. Remember, guys, that you are not in space. You are on the ground. You are trying to estimate everything based on your best ability, right? It is never 100%. It can never be 100%. So you have a certain, we can say the difference from 100% that you can account for as uncertainty, that you are not certain for those percentage amount. So within space traffic management, within space situational awareness, we use a concept called uncertainty propagators. Based on the dynamical models that you encounter, based on the forces that you feel in the orbit, those uncertainty, the covariance matrix that you have for each of this position and velocity vector gets propagated to the state that you want to be in. Now that means you either increase the amount of uncertainty by the time you reach the desired time, or you keep doing orbit determination in between, where you reduce the amount of uncertainty here. So the more you do orbit determination, the more you realize that you have lesser uncertainty on the object. So, but uncertainty never goes. It never goes. It will always be there. And therefore you need to propagate it so you have a very accurate solution at the end. Again, maneuver planning. That's an important concept because if you want to avoid a threat, you need to maneuver. You need to get out of its way. Then you have orbit and attitude determination. And this is a completely different aspect that is used here. Completely a different aspect of orbital dynamics that is, I think, warrants its own presentation and lecture in its own right. So that's why I'm not going in depth in this lecture within orbit or attitude determination. But remember that the ground-based telescopes, the ground-based radar systems, and the radio systems that you have, including the GPS satellites that you have, can track the orientation of the satellites in space with um, meters accuracy, centimeters accuracy, even millimeters accuracy if your sensors on board are very good. Having said that, let's look at dynamical models. Now, I have been saying about dynamical models since the start, and I think that this is very important to understand because this form the basis of how your object moves in space. Now, to the left, you would see a potato-shaped object. That's Earth. So Earth is neither oblate spheroid nor a sphere. It's a potato. That's how it looks like. This is a bit exaggerated image, but the intensity of each of this color that you see here is very well justified based on several space missions that were specifically designed to determine the gravity field of Earth. I think some of you might even see India there based on the screen resolution you have. You could see the Himalayas are in green. Why do you think that that's in green? What does it indicate? What it indicates is that there is a higher central attraction happening at that particular point compared to Indian Ocean relatively. So some of these points that you see, the red one, the pink one, and the yellow ones, these are all varying degree of attraction as experienced by a satellite. I'm simplifying it here, but there are several books and materials that are available on the net if you want to look at geopotential models. That's why I mentioned the keyword as geopotential here. And the next one is a third body. What is a third body? You have Sun, Moon, Earth, Sun, Moon, Venus, Mars, and then you have Jupiter, also Saturn. All of these exert a particular gravitational pull on the satellite when it's in space. And if you are in, say, geostationary orbit, a geosynchronous orbit, or even if you are in the GNSS orbit, somewhere around 20,000 kilometers or so, you would still experience these particular push. And these are to be a pull, sorry, not push, pull. And these are the ones that are important when you're considering higher orbits for collision avoidance, because each of them have a significant impact on the accuracy, the precision and the accuracy of your orbit propagator. The lesser known concept of dynamical models is tidal models. And that's mainly because they don't have much impact on the satellite itself, much impact on the gravitational field. However, they influence the gravitational acceleration that you feel once there is any sort of tidal motion or ocean tides, anything of that, anything that can increase the mass of that particular surface on Earth. That is accounted as a tidal force. And those tidal forces also have an impact on the acceleration and therefore velocity because of integration. And again, if you integrate over time, you have position. So it affects the position of the satellite. Yeah, so these optical illusions that you're looking at, so these are not optical illusions. These are Earth, which are represented in a mathematical format. So when you are using any flight dynamics library, in Python, in Julia, in C++, doesn't matter. All of them have a force resolver inside. Those force resolver use a particular degree and order of gravitational models. It depends on how well the system is calibrated for development, but the underlying geopotential model uses this particular equation. As you can see, the red circles that are around R, beta, and lambda, these are the polar coordinates. So imagine you are at the center of the Earth and you are looking at the surface of the Earth. Now, because Earth is not a very smooth surface, it has bumps on it because of mountains, valleys, rivers, seas, blah blah blah, doesn't matter. These these points represent the exact areas where you want to calculate the acceleration, right? And now some of you might have even noticed the AE part in the first summation, within the brackets of the first summation. That AE represents the radius of the Earth at that particular point. Now, there is a reason why geopotential model is also used over the oblate spheroid model, the not a sphere concept that we have learned in geography in our schools, right? These gravitational models use that particular flattening of the pole, bulging of the equator as the reference, and on top of that, they emboss the impact of each geophysical features, like the mountains, like the valleys, like the oceans, and etc. Now, why am I showing you this particular equation? You might have seen the equation GMM by R square as the common gravitational pull, right? But here, it is not as simplified, because when you want a highly precision orbit, you would want to include all the mass differences that is happening on the surface of the Earth. And therefore, this equation accounts for something called spherical harmonics. The spherical harmonics are mathematical functions that are used to describe and model different phenomena over a surface of a sphere. So in this context, spherical harmonics are used to represent the variations, which is anything like a mountain or anything. So Earth's gravitational field, as I mentioned, it's not a uniform structure. So some places you would have a higher gravity than in some places. Though you as a person might not feel it, but anything in free floating space would be able to figure that out. So you could consider these optical illusion looking balls here as the degree at the degrees and the orders of this coefficient, the blue ones. I think I can show it here. Laser pointer, yeah. As you can see here, yeah. The CNM and the SNM, these are the coefficients of the gravitational potential model. And these are derived from certain gravity models here called Eigen 6C, XGM 2019. These are all derived from several space missions, right? So each of the space missions have some sort of highly sensitive payload on board, like ring laser gyroscopes, or even specific laser. I might not be accurate here, but there are some laser-based methods that can. I think it was the Grace mission or the Ghost mission. I'm not sure. Either one of them. They had a very high resolution approach to figure out what region of Earth has a higher gravity field, higher gravitational acceleration. So if you put in the specific order and magnitude and you say that, hey, I want my gravity field to be very accurate, so you can just increase this to maybe 300, 400, the N and M value, and you can still get a very high, very precise gravity model, though your computation time is going to be significantly high. What did I mean by WGS 84 here, or EGM 90, EGM 96? So WGS stands for World Geodetical Survey of 1984. In this, they came up with the spherical model in which they mention accurately on which latitude, longitude you have what's the radius of the Earth. And that's actually important because this AE is useful here in this particular equation. And based on this, you have the gravity field mapped out. Having said that, let's look at the solar radiation pressure and drag. These are fairly simple in its concept, but extremely difficult to model as well as implement in real life, because you need to know exactly how the satellite is modeled in real life. So certain, like the dish antennas on top of the satellites, have a particular profile, a cross section. So if you have more solar radiation impinging on top of those dish antennas, you have a higher drag model because of ionospheric drag or even photonic drag. So those kind of concepts are a bit hard to model in numerical terms, but certain flight dynamics libraries already exist which come with certain concepts like box and solar panel. So you can represent any satellite as a cuboid with few of flat sheets around, which could be considered as a solar panel based on their coefficients, like the reflectivity coefficient, the absorptivity coefficients, or the what is the other one? Diffusivity coefficients. So the more sparkly and the shining one have a higher reflectivity one. So it's easier to model the force vector in that case. Higher orbits have no air drag, definitely. So this is pretty much limited to low Earth orbit only. And as you can see, with drag, the trajectory of the satellite would actually fall into the Earth. So orbit with no drag would have a pretty simpler orbit in that case. But it's not as simple when you have something called space weather events, SWE. So whenever you are in a higher solar activity time or moment, you will experience the expansion of the atmosphere, the ionosphere, and that is significantly affecting any satellite that is flying in that particular part of atmosphere. It will not be much as that of troposphere, of course, but the amount of drag that you would experience would be significantly higher when it's in a solar cycle, whenever there is a solar event, like a coronal mass ejection, or if it's just a higher solar activity part of the 11-year cycle. So you need to model the space weather events or space weather models in such a way that you use certain indices. There are certain indices based on wavelength of the radiation that is impinging into the atmosphere, like F10.7. Then you have geomagnetic index, basically. Multiple indexes are called indices. And these geomagnetic indices can actually give you a better representation of the density of the atmosphere. Then you use that density to calculate the drag that is applied on the surface of the object. This can also affect the way the satellite is oriented in space. Sometimes it can just fall off the orbit, like it happened with Starlink last year. Like 42 satellites just went off the orbit because of a massive solar event. Yeah, so something like that can easily happen, and therefore you need to model all of that frequently. Now, you might have again heard one of the other frequently used word in this lecture is called covariances and uncertainty. Now, what is covariance? Covariance is basically a stress. It's a tensor. It's an area that is affected by the three principal axes, right? So as you can see on the left, it's a matrix of sigma, I can say, in all principal directions, x, y, and z. And the rest of the non-diagonal elements represent the impact and the influence of each of these axes on each other. If you sketch it out in a 3D plane, in a 3D environment, it comes out to be an ellipsoid. An ellipse in 3D format is called ellipsoid. And this is a very important concept when it comes to collision avoidance in terms of conjunction analysis and anything that has to do with space situational awareness. Because this is a sphere of uncertainty, an ellipsoid of uncertainty. You don't know where the object is within this. It could be anywhere here, 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 here. You don't know. And therefore, you just take this ellipsoid as whole. And then you perform some sort of conjunction analysis here. And what is that? You have a chaser, which might be the blue one. Let's consider blue one to be the bigger uncertain object, could be a chaser. The white one here is the target. Now you're looking at that there is a almost 100% collision probability here because both of them are within each other. But there is a reason why I put this particular photograph, because this particular image, because this is one of the flaw in the way the uncertainty is computed in the current industry. So in the next slide, I will show you the difference between these two. Okay, here you have the uncertainty ellipsoid in 2D as well as 3D. There is a reason why one considers a 2D and one considers a 3D ellipsoid or ellipse in space traffic management. If you are in low Earth orbit, you are not going to hang around for a long time with the chaser. You're just going to whiz past them very fast, like about 16 kilometers per second. That is the relative velocity that you would encounter. As you go high in the orbit, beyond 2000, 3000, even 10,000 or 20,000, you would realize that the relative velocity stops at 4 kilometers per second. If you go to geo, it could even be few meters per second. That's how slow the encounters happen. So they spend a lot of time comfortably within that ellipse. So the concept of uncertainty drops significantly when you go to geostationary or geosynchronous orbit. On the left, what you're looking at is a conjunction ellipse in the encounter plane. So when I mentioned the time of closest approach, I mentioned that that is the point where the object is potentially about to collide or not, if you remember. And that particular point in time is mapped out into an encounter plane. As you can see, this could be the target object within a sphere. This is the chaser orbit object uh, in the in the encounter plane. Then the intersection of that, the one which is considered as black dot here, is considered to be combined and projected spherical object. Now that is important because probability of collision is computed based on the diameter of this combined region. If that intersection is large enough, you have a higher probability, you have a very low probability because it could be anywhere within that region. But the threat is very high. Now, the combined and projected n sigma, either 3 sigma covariance ellipse or 2 sigma or even 5 sigma covariance ellipse, it depends on the accuracy you are interested in. On the conjunction ellipsoid side of things, you see the 3D version of this object. You see the encounter plane, you see the target moving into the sphere, and that is being intersected by a larger sphere of chaser. Now, the combined region of that is the black ball that you see here. And the velocity at which they go past each other or they encounter each other is called relative velocity. This is an important term when you're considering fragmentation events or collisions in space. If there are high relative velocity, higher fragmentation particles you would see happening in space, like 2500, 3000, 4000, even 10,000 particles coming out of the collision. This is an interesting concept because this is defined whether this defines whether the object is actually under threat or not. Now, just to verify and just to make it much more simpler, the high relative velocity that I mentioned just a few seconds back is considered as part of the short-term conjunction because you are there for few seconds and then you're off. And therefore it can be considered as a linear motion. It is not under any gravitational perturbation or anything at that particular epoch. So you can consider the probability to be a simplified Gaussian and statistical type. But on the other hand, if it's at a higher orbit, you are also moving slowly. The collider is also moving slowly. And in that case, you both are very comfortably together at in certain closeness in proximity in the orbit. And therefore, it's a long-term scenario that you're looking at. It could even go up to weeks. In that case, you either go for 3D probability distribution. So when you consider the along track direction in the direction that you're flying, or the missed distance. Missed distance is the no-brainer, and most of the companies currently in Europe, in US, everyone uses this missed distance as a criteria for selecting a threat in space. Now let's come to the major one. It's called collision avoidance maneuver. This forms the basis for risk mitigation within space traffic management. On the left side, you would see the axis R, T, and N, and W, R, T, N, and T, N, W. Yeah, sorry, my mouse is malfunctioning. So you have T, which is in the direction of the velocity of the object, S in the cross track, which means in the perpendicular to the orbital plane, and R in the radial direction, in the opposite radial direction. Same way for T and W reference frame. There is a reason why these two reference frame I have put it here. I'll come to that. Now let's look at the types of maneuvers that you perform. For someone who asked what maneuvers is like I mentioned, it's to prevent any collisions, prevent any sort of, or potentially go to another point in space, because that prevents any sort of collision, or you want to just go there in space. That's it. So the effort that you make to go there. Now, there are three types of maneuvers that can be applied for collision avoidance in general, and one of them is impulsive. What is impulsive? It is a very gross approximation of a propulsion system which fires for a finite period of time. In this case, it could be for a half a second or even less. Anything less than 10 seconds is considered to be impulsive most of the time, because it is not significantly affecting it's not getting significantly affected by the dynamical models as such. It's mostly chemical, so low specific impulse propulsion system mostly, and it generates extremely large delta V. It can even go to 10 meters per second if you want. So it depends on the time of firing. It's almost instantaneous. The reason why I mentioned almost instantaneous here is mainly because when you're modeling it in software, in Python or in any flight dynamics library, if the thrust firing time is less than 10 seconds or 5 seconds, it's usually modeled as an impulsive maneuver. In reality, there is no impulsive maneuver that exists. Everything is a constant thrust maneuver. Now, having said that, let's go to the next one. Constant thrust maneuver or low thrust maneuver. Um, this is a long period maneuver. So this happens over hundreds of seconds. Sometimes even for 3,000, 4,000 seconds, this can happen. Depends if the satellite is having an electrical thruster. And the delta V that it produces over that period of time is also significant. It's cumulatively large. And you could say that some of the spacecrafts that went into deep space carried with them the electrical thrusters on board, which were firing for months at a time. So the cumulative delta V was significantly high. So at that instant, it would be way less than a sheet of paper falling through air. And this is significantly influenced by dynamical system, because they normally go around the orbit for a long period of time. And of course, this is a new space favorite because they say it's more fuel efficient and it can be packaged into a CubeSat, so it's easy for anyone to design a spacecraft with electrical thrusters on board. Now, differential drag maneuver. This is where the attitude of the satellite comes into picture significantly, because here you don't use any propulsion system like these two. And it takes a very long time to actually make an effect. Like you can see here, this is the nominal drag, which means it's in a drag configuration where there isn't more drag on the body. So it can easily coast through the environment without any problem. But as soon as it has to slow down, it will change the drag configuration such that it will slow up to, it will brake to speed up, and slow down to, speed up to slow down. So this is a type of maneuver that normally you can see in low Earth orbit satellites, because anywhere above, it's of no use because you don't have air. And the best combination would be to use differential drag maneuver alongside constant thrust, because you can fire the engines for some time and then you can coast beautifully, and you can carry out your mission however you want to, and then you can go back to firing the thruster again, and so vice versa, however you want to do that. In that way, you reduce the amount of mission impact, so you can continue to produce data, make money out of it, and go ahead with that. And differential drag maneuver always acts on the T and W reference frame, because this is directly acting and dependent on the velocity vector of the object. So that is why I mentioned this T and W here. Anywhere else, a simple RSW reference frame would work. Having said that, let's go to the effect that you would see at TCA. TCA is a time of closest approach, the danger zone, whatever you want to call it, the area that you have to avoid. Now, these are the areas that you are thinking about performing a maneuver. So you generate all possibilities of maneuver, these blue dots, white dots, and everything. You generate all possibilities of maneuver in the maneuver search space. When I say maneuver search space, It is basically a space full of all possibilities of maneuver, whether good, bad, ugly, doesn't matter. All maneuvers are found within that particular maneuver search space. So you, based on whatever criterion you have, say you have an electrical propulsion system, you have a chemical propulsion system, and you say that I will only maneuver during weekends or only during weekdays because I want TV connection on Sunday, Saturday, then all those conditions are taken into account, and then you perform a maneuver which would go in this direction. So if the original dotted line that you see here were about to collide with the chaser, a maneuver performed here in any of these direction would potentially avoid that collision. And this is the idea of a collision avoidance maneuver, as simple as that. And one should understand that the industry standard at the moment is always fire the thrusters in the direction of the flight, never in the radial, it means towards Earth, or in the perpendicular to the orbital plane. Main reason is you are saving fuel. You are already using your velocity to your advantage. Why not just fire up in the same direction that you're flying, so you can just avoid the object completely? And the process starts all over again, where you have performed the maneuver. Now everyone starts looking at whether you're going to cause any more conjunction again. So there are some libraries that you can use for modeling spaceflight dynamics in general. One of them is STK, as some of you may already know. And there is something called Free Flyer. Free Flyer is pretty fun to use for mission design and stuff. There is NASA's Kara, and this is a tool which is predominantly used by Canadian Space Agency, by NASA themselves, by Mexican Space Agency, by Japanese Space Agency, and I think even more, because it's a widely used and tested tool, and it integrates so well with Microsoft Excel that no one wants to develop a tool around it. Then you have SatNogs. SatNogs is a open source ground station network that is provided by Liber Foundation. This can give you two-line elements of different satellites that are already available for you to perform orbit determination on. Again, if you're performing an orbit determination with two-line elements, it is not worth it because it is a mean Keplerian elements that you're looking at. It's not a perturbed state vector. EUSST is the European Space Surveillance and Tracking Network, and this is I think a consortium of more than 26 or 30 telescopes and radar stations across Europe, and they provide constant conjunction alerts with very high degree of accuracy. Now, the other two here on the right are flight dynamics libraries. I have personally used ORCID extensively to develop several tools, and this is one of the most open source and free and one of the most wonderful flight dynamics library that exists, and it's still under production, which means it's an active community. And recently ESA launched something called GOROT, General Orbit Determination. I don't know what OT stands for, but yeah, this one is just, I mean, after 10 years of development, they just released this out. It's for free, and I guess with a bit of access control, you can do basically any orbital mechanics stuff with this, even orbit determination. And I should say that when I tried GOROT against ORCID, this was roughly 200 times more powerful and fast compared to ORCID, because this is completely written in C and C++ with Python wrapper. This is written in Java with Python wrapper, but there is the communication of another library in underneath, which takes more time. Yeah, so the final topic of space situational awareness itself is the uncertainty reduction. There are two types of uncertainty. One, randomness because of your system. You might be using a bad optical telescope or a very good optical telescope or a very bad radar system. All of that introduces a type of bias into the system that can prevent you from doing accurate observations. And you have to account for those uncertainty by testing rigorously. There is another one, which is knowledge based. You can only know what you know. What you don't know, you can't know, right? So that's a problem with epistemic uncertainty. And how do you do that? You perform more research. You perform severe amount of research, or maybe even a prediction algorithm that can actually help you with reducing that knowledge uncertainty based on historical data. And how do you reduce that? Through variable cadence or frequency of observations and dynamics. So you have improved sensing and tracking. Then you have accurate models. You can use that to reduce uncertainty. Within data processing, you can do data fusion from several sensors, the multimodal approach. Then you have the on-orbit determination or on-orbit estimation. So you can use GNSS sensors on board the satellite, which can do even carrier phase measurements, which means it can provide accuracy, precision up to centimeter level, not accuracy, but precision up to centimeter level. Then you have regular updates and correction and machine learning approaches if you are interested in applying machine learning for this. And those are some operational procedures. So these are influencing the way you are performing the operation itself. Now, what is the future in this? Future within machine learning, there are several, and I think it's at the right time that the machine learning is also evolving. One of them is within orbit prediction. The other is anomaly detection. What is anomaly? If you are observing a satellite and suddenly for some time you see the sudden change in the satellite's orbit, you could predict either the satellite has performed a maneuver or not. So the ability to get that anomaly satisfied within the detection paradigm, that is being facilitated by machine learning and artificial intelligence. Space weather prediction. That is a very important one because the space weather data that we get most of the time from open source is not that accurate. So there are some entities which are doing active observation of the space weather phenomena, but you need to pay them. So machine learning is applied. The concepts of physics-inspired neural networks or physics-based machine learning are being used actively within the space weather prediction area. Automated tracking and correlation. Now, that is just basically maintaining of catalog. You are observing a bunch of objects in sky. You don't know which objects these are. So based on the existing data and based on the spectral response, you start to develop a database on which you can apply machine learning to figure out if this is the right object that you are tracking. It increases the speed at which you can perform orbit determination. In situ is basically sending a sensor up in space to do all the um, reduction in uncertainty that you want. So one of them is telemetry. So sending the data constantly of its position and velocity at the same time to ground. The other is space weather sensors. I think there is one Indian company which is already doing that. I think it's called Digantara. They are already trying to get space weather information through in situ observations. Active debris detection. This is based on one of the satellite mission that I worked on with the European Space Agency, and that was to get the active data on satellite debris through impacts on the satellite based on a dust counter. There is LIDAR and INSAR. So some of the companies have already started to work on the idea of using LIDAR within the space situational awareness to detect small, very small, minute debris, and also interferometric synthetic aperture radar principles are being applied to prevent or to detect any sort of close approaches. So that about concludes the presentation that I had prepared for this lecture. Unfortunately, I couldn't go into deep dives within each of the concepts that I presented here. Otherwise, we would have to stay here for the whole day. So I think I can conclude my presentation here, and thank you for listening patiently, and hope you have questions that I can answer.
All right, yes. Thank you so much, Abhinav, for this wonderful session. And these guys, just in case if you're having any kind of doubts, you can ask Abhinav right away. And after that, I'll just share a quick way through which you can register for this particular training program if any one of you is interested. Okay. But before that, if anyone is having any kind of doubts, please feel free to ask it. You can maybe unmute yourself by raising your hand, and we'll take your questions, or maybe in the chat. So yes, guys, any kind of doubts? All right.
Seems like
Okay.
everyone understood it. Ah, okay, cool.
Okay. Okay. Yes, Akanksha, you can go ahead.
Yeah, thanks, Mark. It was a great session, and I would like to know more about the European Space Agency project which you mentioned now.
Okay, so when I started my master's at TU Munich, I was introduced to one of the project that could potentially be a satellite mission. So that was to detect sub-millimeter debris or sub-centimeter and sub-millimeter debris in the low Earth orbit. Unfortunately, like I mentioned that in the one of my previous slides, I think I can go back there. Yeah. Um, yeah. So in this particular map, as you can see that the number of objects that you are looking at is more than 20,000, right? But these are the ones that are actually trackable from Earth. So you don't need to send anything up there to check what's the actual count of these objects. But if you are going below 1 centimeter or even below 10 centimeter, your radar system starts to falter. You're not able to figure out if that is actually a debris or just some anomaly on the radar because it's going below the signal to noise ratio that you're getting back on the radar. So this mission was to alleviate that problem. So we would send a couple of CubeSats in a swarm method, and that could carry three payloads on board, three dust counters on board. And these dust counters would go in the region of highly populated sub-centimeter and sub-millimeter debris, and it would be impacted by that while maintaining a constant trajectory, which means you needed an active AOCS on board. And therefore, this mission was to actually bridge the gap between knowing the number of debris particles that are available under 1 centimeter or 10 centimeters through impacts. Now, this is used in reducing the uncertainty from a knowledge standpoint, as I mentioned earlier on. So that's the mission that I worked on, and I think it's about to be. I'm not exactly sure because since I graduated, there has been there's some improvements into the project, and I think ESA Space Debris Office is actually helping them at the moment, I guess.
Okay, thanks a lot for explaining.
No worries.
Yes. Any more questions? I had seen one more hand that was raised. Anyone else would like to ask a question?
Uh, my
Yeah, please go ahead.
uh, Abhinav sir, first of all, I thank for the session. So my doubt is regarding the space debris and the stargazing, because while stargazing from low light pollution area, we will be able to see some satellites which is falling from the skies. But some may think it is as typical meteorite falling from the sky. But how can we differentiate satellites and meteorite shower at the time? Because more satellites have been now inactive in this Earth's orbit, but we don't know to how to differentiate between the meteor shower and the satellites falling.
That's a really fantastic question, actually. That's the same question that I had when I was doing my master's. So there are, as you know, some of the observatories which are in Chile. Um, I forgot the name, man. I think it's in La Silla as well as La Palma, I guess. This these observatories, they have a they have a high aperture telescopes. Some are in meters level. So based on the light gathering ability of these telescopes, right? They uh, they they are able to look at dimmer objects with higher magnitudes, up to even 30, for that matter, apparent magnitude up to 30. So what you're talking about as the differentiation between a meteor shower versus the defunct satellites versus space debris. Now, out of these three, two of them are pretty well known for modeling these orbits. Most of the meteor shower that you're looking at, they are already very well modeled by minor planet centers, by astronomical unions. So you don't have to worry in terms of knowing which part of the image you're looking at and if that is actually a debris or a meteor shower. If it is a meteor shower, the tracklets that you're getting from observations, from the astronomical observations, it will automatically sense that and detect it based on the orbital motion of these objects as well as the defunct satellites, because these are very well being tracked. Because they are not active doesn't mean that the ground stations are not able to track. They will be able to track it regardless of that. So once you know these objects, you can safely disregard anything that looks or remotely even looks like those objects in the image. The leftover ones are just unknown tracks. The astronomy society cannot understand what these are. Now, these are usually discarded as waste images because these are reducing the science output of these astronomical societies. Now, this is exactly where one of the future approach that people are experimenting with using machine learning comes into picture. So machine learning can recognize, based on, I mean, statistical data can recognize certain spectral response based on continuous radar tracking, right? So when the images were taken by the astronomical telescopes, they already know which part of sky they were looking at. So they know which part of objects were going through in which grid in that image. Based on that, you can create your own most accurate high fidelity orbit propagators. And based on the last known position of these objects, you can automatically start doing orbit determination of these objects. And that's how one could figure out if it is an actual debris or if it is actually a satellite, defunct satellite that's going on. Does that answer your question?
Yes, sir. Thank you, sir.
No worries.
All right. Any more doubts, guys? Anything else? All right.
Okay, I guess Rohan, this is it.
Okay. All right. All right. So I'll just go ahead and talk about how, if you're interested and if you are someone who is willing to enroll for the astronomical, not astronomical, but the fundamentals of astrodynamics with Python and Spartificial. Okay, I'll tell you how you can do it. If Abhinav, you can allow me to share my screen.
Yeah, just a moment. I was just
Yeah,
removing that. Do you see my screen yet? No, right?
No. I'll just go ahead and present my screen.
Go ahead.
All right, guys. So I hope my screen is visible. So what you have to do is you just need to go to spartificial.com. Okay. So once you go to the spartificial.com, there is an option of programs. You click on that. And then that's where you can see the fundamentals of astrodynamics in Python. And that's the June batch. So this is going to start from 12th of June. It's going to be for 8 weeks long, where you will be learning different concepts like basically the fundamentals of the astrodynamics and how different concepts like two-body problems, three-body problems, simulating a whole solar system, how you can determine the exact position of a particular satellite based on the previous location, just like Abhinav had mentioned a while ago. All that kind of stuff is packaged well in this particular whole program of 8 weeks, including the machine learning concepts. So the last week, basically like about 1 or 1.5 weeks, is dedicated towards the machine learning. And once, if you are performing really well throughout this training program, you will be getting opportunity to get selected for the research internship. And now this internships would be focusing mostly on the concepts of the machine learning, where we'll be giving you some kind of projects to work on to strengthen your concepts of machine learning. Okay, because as even Abhinav had mentioned that it's some of like one of the things that is widely used in this particular field nowadays, right? So yeah, this is the kind of thing that we are providing, and this is the overall fees for this program. It's 4,719 in Indian rupees. And over here, you can just browse through all this kind of other content that we are going to provide. All right. And the way that we're going to measure how you are performing throughout this training program will be with respect to two assignments. All right. We'll be providing you 2 assignments, and you need to score about there is some kind of a mark through which you can, if you will be scoring above that, you will be selected for the research internship. So yes, all that kind of stuff would be explained in a much more better way once you join this particular program. But yeah, in case of any kind of doubts regarding how to register, you can ask me right away, or else just in case while registering, if you're having any kind of issues, there is always an option of contacting us via WhatsApp, or maybe if you want, you can also email us. I guess it's mentioned at the end over here. Yes, team@spartificial.com. All right, guys. So yeah, that's how you can simply go ahead and register for this particular program. So yeah, any kind of doubts regarding this, you can ask me, or else yes, we are done for the session. Anything you would like to add on top of this, Yash?
No, I guess, Rohan, this is it. And yeah, along with the Astrodynamics program, we have Astronomical Data Science program as well. That is focusing more on the image processing in deep space and machine learning as well, focusing more on the computer vision skill sets and tool sets. Yeah, we can go through that web page as well. Yeah. So this program is going to start on June 26th, and it's a 10-week program, and the internship criteria and everything will be seen. Yeah, finally, I would just like to thank everyone for joining the session, and thank you so much, Abhinav, for conducting this session and the awesome information that you provided about astrodynamics and space traffic management, the awareness, and all the stuff that is going on regarding